Testing. Okay. So now that we've watched that video, let's kind of pick up just some written notes. Again, I'm not going to read directly off the slide, but let's do a recap of some of the things we talked about. So what we now know is that it's actually electrons that are able to move through materials. It's not the protons. Ben Franklin was wrong. He just took a stab at it and he thought that positive stuff moved. 50-50 shot at it, right? It's actually the electrons that move. We know that now. And so really the terms I need you guys to know are mainly this one here, insulators and conductors. Right? Things that want electrons and they like hold onto them so tightly that they never let them move and flow. Those are your insulators. If I were to put some more like written notes on here, they hold on to electrons, the insulators do. Right? The styrofoam block that I had sitting there before, it held on to those electrons. The natural thought that some of you had was the electrons went into the metal. They didn't. The styrofoam kept them. Okay. Other things, though, they don't hold on to their electrons. They allow the transfer of electricity. And those are conductors, or maybe even superconductors. Really, the difference there is how much resistance they have. You guys ever heard that word resistance before? There's a concept that you would have learned back in grade 9, and it's been a long time, but it's called an ohm. And it's got this omega symbol to it. It's the resistant symbol. Certain things are more resistant than others. Like copper does not have a lot of resistance. It allows electrons to go through it fairly easily. Anyways, depending on how good it is at conducting electricity, it could be a superconductor. Okay. Here's a picture that I've got that kind of even has just like some generic examples. And you guys probably know some of these things like tinfoil or nails. Those will conduct electricity, right? But like, what about a tree or a bicycle tire? You guys know that like rubber doesn't conduct electricity, right? It holds on to its electrons too tightly. But there are some things that are in the middle. And I didn't mention that on the last slide, but those are called semiconductors. That's listed right here. And semiconductors are really cool because sometimes they conduct and sometimes they don't. And it really depends on the properties around them. The classic example is a photocopier. So here's how a photocopier works. You put a piece of paper on top, right? And that little light shines along the bottom as it scans it. Well, you know what ends up happening is light either goes through the paper or it doesn't. And if it doesn't go through, it's because there's writing there. Does that make sense? And the presence of light either activates or deactivates these semiconductors because they can conduct electricity depending on the conditions. Selenium is actually what's used in photocopiers. If there's light exposed to it, it conducts. If there's no light exposed to it, it doesn't conduct. That's actually why that light goes along the bottom there. Kind of cool. They can also conduct sometimes depending on temperature. For example, anybody ever try to start their car at -40 and their car doesn't start? The only variable that changed is the temperature, right? And so some things don't conduct as well depending on the temperature changes, right? So if this ever comes up, not that I'm not going to test you specifically on this, but the most common semiconductors are here: silicon, germanium, and carbon, and usually anything in that metalloid part of the periodic table. If you guys know much about your chemistry, right? The metalloids are like sometimes metals, sometimes nonmetals. They have the ability to sometimes conduct. Okay. Electronics in general need semiconductors because do you want your phone on always? Or do you want it off once in a while, right? We have switches for that, but semiconductors can do that as well. For example, I have a thermostat that when I walk by it, it senses me and turns on. Does that make sense, right? Like just recognizes the motion, right? I imagine it must involve some sort of semiconductor to change the circuit there. And an environmental condition changed, light or heat or sound or something like that. So anyways, here's the superconductors. Superconductors are so amazing that they lose no energy whatsoever. However, although we know that cold sometimes slows things down, sometimes we actually need to be at absolute zero temperature, like with liquid nitrogen. There's a lot of research being done these days into like magnetic levitation trains. Everyone ever heard of those before? It's like where the train basically rides on a magnet, and the train is a magnet as well, but it's flipped the other way around, right? And that way it should levitate. It's called maglev technology, right? And so, oh, fantastically strong. Yeah, it takes a lot of Teslas in there for it to work. That's the unit of magnetism, right? Yeah. But like that's what I found in this picture right here is that sometimes it actually works better when it's really cold, and you have to have a superconductor used with liquid nitrogen. Okay. Again, that's not really the point here. Like I'm not going to assess you on that sort of stuff. We need to be able to apply this knowledge. But those are the 4 categories I need you guys to know. Okay. Now, what we witnessed sometimes was something called the separation of charge. And I already did this little activity where I brought a negatively charged object near that little hanging ball. That's called a pith ball, by the way, in case you're wondering what it was called. It's called a pith ball. And we'll use them in an activity later. Okay. Well, that pith ball, remember how I told you that I sprayed it with graphene? It's neutrally charged. There was really like an even amount of charge. It wasn't positively charged, it wasn't negative charged, it was exactly neutral. And in theory, it should be like kind of spread out. Well, then I brought the negatively charged black rod next to it. And you know what ended up happening? It attracted to it. And I can explain why. Well, the negatives that were inside, remember how the styrofoam was an insulator? Which means it holds onto the electrons, so they weren't able to go through the string and through the wood out of there. But the outside was coated in the graphene, which is a conductor, so the electrons have the ability to move around a little bit. You know what they did is they moved. All of the electrons moved as far away as they could from the stick as it came closer to it. But you know what that ended up happening? It caused a separation of charge, where all of the electrons were on the opposite side. That piece of metal, by the way, had the exact same thing. All the electrons rose to the surface of the piece of metal. But hey, hang on, what happens when that occurs? Then the negative and the positive right here, they attract. And that's why that little ball eventually sucked its way in and touched the little the rod there. Let me show you this one more time again, just to remind you. Where's the stuff here? There's this guy right here. And where did I put that little ball thing? I got an extra one here. So here, do me a favor, just hold that real quick. Right. Hopefully what we're going to witness here, if you guys can see it, maybe hold it up a little higher, would you? I'll just have you be the holder there. So try to hold it as steady as you can. I'm going to apply a charge to this. So I know it's moving around a little bit. Let's see whether I can make this thing kind of move towards this charged object here. It'll suck towards eventually. There you go. You guys see how it came towards and it sucked towards, but then it pushed it away. Why did it push it away? Well, all of the electric charge that was on this thing right here, as soon as it touched it, it gave some electrons here and some electrons here. They're both negative. What do 2 negative things do to each other? Repel. So if I touch it one more time, hopefully it'll like, there we go. Now I can get it to kind of like move like this. That makes sense? So the term I need you guys to know at first, though, is separation of charge. This neutral object, half of its electrons kind of like went to the opposite side, and it had like a dipole into it. If you guys know anything about like chemistry and dipoles and how you have like 2 opposite sides together, magnets really work the same way, positive and negative ends. Okay, that's what this slide here kind of talks about. It just discusses how it got to that point. So if you just want the terminology on it, this black rod, as I was rubbing the fur on it, there are now more electrons. The electrons went from there to here. If I wanted to, this doesn't work quite as well, but silk actually does the opposite. If you take silk and rub it on glass, you can actually take the electrons off of the glass, and you can make that positively charged. The only reason why I didn't do that in class is that the silk and glass one rarely works all that well, but the electrophorus that I showed you, where I did like my finger on there and I zapped myself, that one actually is a much better way of getting a positive charge. Okay. For those of you guys who take chemistry, maybe you'll recognize this term. It's called electronegativity. You guys ever heard that term before? It's an affinity for how much something wants electrons. Fluorine, if you know about this, fluorine is a 4.0 usually on the electronegativity chart, which means it really wants electrons. Whereas like hydrogen, I believe, is a 2.2. It kind of wants electrons, but less so, right? And I believe sodium is like a 0.7 or something like that. It really doesn't want electrons at all. Right? It's a similar concept to this. There are certain things that want electrons and certain things that don't. So let's recap. If you really want electrons, are you an insulator or a conductor? You're an insulator if you really want electrons, because you hold onto them so tightly that no one else can have them. But if you're okay with sharing them, then you can make a circuit and have it go through a loop. Here's kind of a table that you might come across. That it's not necessarily like electronegativity on the periodic table, but it basically lets you know who wants to have negative charge and who doesn't, right? So these are things that are able to accept a negative charge. These are things that are more likely to become positively charged. So what we did as well is we did things like conduction. The term conduction means that you actually have two objects touch each other. If they actually physically come into contact with each other, then charge can move. Now this is kind of an old-fashioned diagram because look, all of these charges are positives. But like, do positives actually move? No, it's actually negatives that move. And so sometimes you'll hear something called conventional current, and that's where we use positives instead of negatives, and only because Ben Franklin thought that positive moved for the longest time. But like, just flip it in your mind, okay? So I know this says there's positive charge, but imagine this is a charged object and this one's not, right? And you touch them. Well, all the charge will move from one to the other. Not only that, it's gonna like split it equally, right? Like if this object and this object are the same size, they'll both roughly take the same amount. But you know what's gonna happen immediately after they touch? They're gonna separate. Because now you're positively charged and you're positively charged. What do positive things want to do with each other? Repel each other. Right? But let's talk about this initial one right here. Why did this get sucked towards? Imagine that this had equal positives and negatives. So I'll try to make like an equal amount of positives and negatives here, right? As this positive thing gets closer, what's really going to happen is all of the like charges will go to one side, all of the unlike charges will go to the other side. That's separation of charge, and then these things would actually attract it first. Hopefully that's what you noticed with the pith ball. When I brought the wand close to it, it got sucked towards it, and then immediately it kicks it away. Yeah. Well, like separation of charge is where you bring a charged object close to another one, and it creates a dipole. You ever heard that phrase before from maybe chemistry? Right, where it causes it to like split into like half and half, right? I don't know. Maybe the silly example would be it's like a grade 7 dance, and all the girls are on one side of the gym, and all the boys are on the other side of the gym. Does that make sense? That would be a separation of charge, right? Now, the opposite of conduction is induction. Maybe they're not opposites of each other, but like they contrast each other. Okay? Conduction is where two things directly touch each other, and the charges move. Induction is where you bring it really close and that separation of charge occurs. That's what this picture here is, right? Here's the same picture. Here is the negatively charged object, and I'm going to bring it really close. Well, what happens? All the negatives go way over here, all the positives go way over here, and I should be able to cause these two things to want to suck towards each other, right? That is known as induction, where you're inducing charges to become different. Okay? What I want to show you in our last slides here is this is actually how you can make things positively or negatively charged. It's actually what I did with that styrofoam block in the electrophorus. So here's a bunch of pictures. Imagine that you brought a positively charged object towards a neutral object. This is separation of charge, right? Boys on one side of the gym, girls on the other side of the gym, right? They separated. But is it still neutral? It is still neutral. Why? Well, because there are 3 negative and 3 positive charges. It's equal to both sides, right? But we've now separated them. But let's do something extra. Let's attach a ground wire. You guys know what a ground wire is? It's like for like excess electrons to kind of go away from. Now, I was the ground wire in the electrophorus because I was the stealer and grounder of this thing, right? So let's say that you attach a ground wire to it. What's the ground wire going to do? Well, since it's not actually the positives that are moving technically, it's the negatives that are moving, negatives will come back up through the ground wire, and a few extra negatives will come back to kind of counterbalance it. Because look, if all these negatives are over here, then there's kind of room for negatives to kind of come up and take their place right here. Or maybe a better way of thinking about it is that these positives right here have pushed these positives so far away that like the positive charges have left. We just know the positives don't actually leave though, right? Now cut the ground wire, which is for me, was me taking my finger off the thing there. Okay. Once you cut the ground wire, now there's a disproportionate amount of charge because 2 of those positive charges are now lost, right? And now we've made ourselves a charged object. This object right here would now be negatively charged. Okay. I got another picture that kind of illustrates the same thing. This one's better though because it uses negative charges, and that's what we really should do because it's actually the negatives that move, right? So, scenario, I bring a negatively charged object near a different object. So this is box 1. It creates a separation of charge. It used to go positive, negative, you know, like a nice split here, right? And what ends up happening is all of the negatives get pushed as far away as possible because negative thinks, guys, You're not giving me your best attention here. If you don't need to be here, go somewhere else. But please, stop talking. All of these negatives right here will push the electrons down the ground wire. They're getting pushed literally away. This is what I did with my body. Okay? If you guys remember the scenario here, the electrons here got pushed to the top of this plate here, and then I touched the plate. The electrons went through me. I lifted my finger off the plate, and all of a sudden, now that this thing is cut, now all that's left is positive charge. And now you have a positively charged object, because you literally like sucked the electrons out of it. Okay. I think that's my last slide, right? Oh no, I had some more. Oh, it was the electroscope, sorry. Electroscopes do sort of the exact same sort of concept. It's a really useful tool. It lets you know whether things are charged. For example, let's say you bring a positively charged rod nearby. What's happening right here? Is this conduction or induction? Induction, yeah, because you're not actually directly touching. And induction causes what we call separation of charge. All the negatives came to the surface, and that left us positive down here. Well, what do two positive things do to each other? They repel. Or let's say I bring a negatively charged rod to the top right here. What does the negatively charged rod do? It pushes all the electrons as far away as you possibly can have. Again, a separation of charge. But if both of these two leaves are negatively charged, they're the same, they repel. Same sort of picture going on here. It's really the same diagram again. And yeah, go ahead. Good question. So let's go back and let's do that diagram again. That's a great question. Okay, so let's do this. Okay, so let's take it from the top here. I did this first. So let's keep track of where the electrons are. Where are the electrons now? On the surface there, right? Was that induction or conduction? Because direct contact caused us to move the electrons from this fur to here, right? Then I brought it near. Now when I brought it near, I better ground it first. There we go, I'm grounding it, right? When I brought it near, it caused the separation of charge, and the leaves separated, right? But when I touched it, what ended up happening is now all of that's now negatively charged, right? I conducted. There's negative charges all the way throughout this thing, and it's separating, right? Okay. Exactly, because what am I going to do? If I touch it now, I'm going to ground it, and all the electrons will go back into me. Right? Now let's make our positively charged object, right? So I'm going to put a whole bunch of negative electrons here. But again, the styrofoam keeps them. So when I put this thing on top, the electrons are not in the piece of metal. But what it's done is the electrons on the bottom surface there are pushing the electrons in the metal to the top, right? And then now I'm going to touch it. And I've now grounded it in a way, right? I've stolen them. And by me doing this, I'm now cutting the wire. Does that make sense? And now there's fewer electrons in there. Push them to the top, I steal them, cut the wire. Push them to the top, I steal them, cut the wire. It would still go into my body, but it wouldn't go through the floor, I guess, right? It's probably, those electrons are probably going onto me, and some of them are getting into the floor, maybe. No. So. Okay, so now let's talk this through, right? All of that is negatively charged, right? And this is now positively charged. What happens when you bring a positive and a negative to each other? They want to attract. So you know all those extra electrons that were down in the bottom there? When I bring this positive thing towards it, where are they going to want to go? Back up. And if there's no longer electrons down at the bottom here, as I bring this towards, we should see the leaves close because I'm sucking all the electrons up to the top surface. That makes sense? Well, so there's two different ways, right? There's conduction, which is where they touch and travel, right? But induction means you can move them around. And if you then cut it in half, well, now you've kind of done the same thing, right? Does that make sense? That's what this last slide here is, right? So let's look at this. This kind of shows the two of them. Here's charging by contact. I literally have a rod that's negatively charged, and I just touch it to it. Well, now it's all negatively charged, right? That's what I did at first, right? But what if I just bring it close, right? In this example right here, what if I bring the negative rod close, but see how it doesn't touch? All of the negative electrons are going to try to go as far away as they possibly can, right? But let's say we actually also have a ground wire. Right? So not only did the electrons try to go all the way down here, but they tried to escape down this wire here, right? Snip the wire. You're now missing electrons. Well, if you're now missing electrons, the remaining thing is now positively charged, right? So there are two known ways of charging something. Conduction, where you literally have them touch, or induction, which requires a little bit more work, right? But that was this whole, right, sort of thing there. But they were really both a way of kind of trying to transfer charge. Good question. That's my last slide now. Okay. Does anybody have any big questions? Okay, there's not a lot we can do with this yet, which is good, because like whenever we start a new unit, I'll face you guys now. Whenever we start a new unit, like I'm just introducing a concept, right? Getting some ideas going. We really can't like do questions with what I've given you there, right? Does that make sense? Like this is just introductory stuff. So tomorrow, I want to give you guys some time to get caught up, okay? Please get a hold of me. Have me help you on your lab or your assignment, right? I expect that you need to ask questions. That's why we're here, okay? Last thought here, and then I think it's time to go, right? 10:25. I got 5 minutes here. I won't use all 5. I don't care when you guys write your test. Like, I really don't. If you want to do it tomorrow during class, sure. If you want to do it in the test writing center, whenever, it doesn't matter to me, okay? I do think that we need to get it finished with relatively soon, because we do have more curriculum to cover. Guys, just give me 1 more minute, okay? But it would really be beneficial, if you haven't written your test yet, to make sure you try to finish the activities in the labs, especially the labs, okay? The stuff we do on the labs will not be on the diploma exam. It won't be. And yet I think it's the most valuable learning I can give you, okay? That's what my experience has taught me as a teacher, is that if you just prepare for the diploma exam, that's fine, that'll help for one thing. But like science, if you go on in science, you don't write tests. Scientists record data, they observe, they make lab reports. Does that make sense? I really want to give you a taste of that. I know you may not go on into the sciences, but like that to me is actually one of the more important things we do, as opposed to just preparing for a diploma. Okay? I want to do both though. Okay? I want to do them both hand in hand. Okay? That's all I got. I do have a few things to hand back. I marked a bunch of labs. So by the way, fair offer, if you didn't do well on the first lab, you can redo it. Okay? It's your first time around. You're learning what I'm looking for. Okay? And if you want me to like pre-mark something and take a look over it and be like, hey Chris, is this enough or is this right? Please ask me. Sound good? Okay, now I'm done.